Okay, this is next example. We going to consider the steel column supporting the load HO. Okay, the P1 is the roof load come from the floor and the joists on the left and on the right for 200 kilonewton each. So the total here gonna be 400 kilonewton. Okay, and for the second floor, the P2 have the value of 2,400 kilonewton. So this is going to be the total of 4,800 kilonewton. The column AB from the second floor to the roof have the area of 9,218 millimeter. And the column BC is for the first floor to the ceiling of, so the floor of second floor is have this area, and the column made with the steel is have the modulus of elasticity of 200 gigapascal and have the yielding stress of 250 megapascal. We now going to find the stress in the segment AB of the column and the segment BC of the column, and we going to determine which one is the maximum. And then we determine the axial deformation, okay, of the NA of the column, the top of the column, with respect to the C that is on the foundation. Okay, let's first draw the free body diagram, determine the axial force in the segment AB and the segment BC. Okay, just cut it like this. If you see the P1, P2 is 400, so the force in the column AB is going to be 400 kilonewton. And for the column BC, we cut it here. We have force here of 400 kilonewton. And over here of 4,800 kilonewton. So the total is going to be 5,200 kilonewton. And next, we're going to find the compressive stress for the column AB. We divide the 400 kilonewton by the 9,218, the cross-sectional area of the column AB. And also we have the stress of only 43.3, which is a lot lower than 250 megapascal. So this is going to be in the elastic behavior. For the column BC, the load is very large, and then we divide it by the area here, and then we got the stress here. And what we have, the stress is larger than yielding stress. This is going to be in elastic or in the plastic behavior. That means when we release the force, the AB gonna recover back, but the BC gonna have some permanent stress. Okay, the maximum stress is going to be in the BC portion of 385.8 megapascal. Next, we determine the axial displacement of A, point A, with respect to C. And if you remember from the mechanics of material, we have the sigma equal to E times epsilon, and then the stress is going to be P over A equal to E, the deformation divided by L. So you're going to get deformation going to be what? P L divided by A E. However, this equation can only use following the Hooke's law. So the AB is okay, but the BC is no okay, because this one is in plastic behavior. We're going to determine the deformation based on the strength that's obtained from the stress-strain diagram. Okay, for the plastic behavior. Okay, we put over here T85.8, and it has the strain of 0.0108 approximately, and then we're going to put the plastic strain into the position to determine the deformation, since strain equal to deformation divided by L. So the deformation gonna be strain times L. Okay, you got this. Put everything together, you get the total deformation of 44 millimeter. Is separate into this part from the AB of the elastic behavior. You can see behavior always have very small deformation, but this one for the plastic behavior. So that is the settlement or the decrease in the height of the point A with respect to C. And then if we release all the forces out, for example, we're going to repair this structure, the AB going to return into its original length. Okay, but the BC is not. BC have the plastic behavior. So let us trying to see how much the BC going to recover. The same as before, is going to return in parallel to the first region, and we are looking for the elastic recovery over here. And since we have E equal to sigma divided by strength, so the strength is going to be sigma divided by modulus of elasticity to determine this. Okay, we have this. It's going to be 0.00175, and this one is 0.0175, and this one is 0.0108. So what we have over here is the permanent set. It's going to be 0.00905, and then since the strain equal to deformation about divided by length, and then the deformation gonna be strain times length. So we have the length of 400 Newton. Then we have the settlement of the column BC of 35 millimeter, but the AB, when the load return, has the 4000 millimeter as before. So the first part, when the force acts into the structure, the point A have the downward movement of 44.1 millimeter. Point B, only the shortening of the column BC, that is going to be just the 43.2. Okay, this is 43.2. That is 44.1. This is the deformation of the BC segment, and includes the deformation of 0.87 of the column AB. Okay, and it's going to be this one. And when everything just release, okay, all the deformation of these two columns going to be 36 millimeter due to the permanent deformation of the column BC. That's gonna take this column down the same as before, even though itself is still 4000 millimeter, but this portion is gonna be 4000 millimeter and then minus 36 millimeter. That is going to be 3970 64. It's going to be just 3,964 millimeter. Okay, the column have different length now. Just to put like this, and this is 4,000 millimeter. Okay, that is the second example for this chapter 4, and next we will talking about the shear stress strain diagram. Next we are going to talking about the shear stress strain diagram. This diagram is obtained by torsional testing of thin wall tube by using the torsional testing machine as shown here. There are some structure in civil engineering that we use the shaft to drill the soil, and we building the pile, very large pile. We also sometimes need to bore the rock to search for water, something like that. So there is some work in civil engineering that we use shaft, and shaft is the same as the one that's beneath the truck, that transfer the torque from the engine to the rear wheel. So when we talking about the shaft, so we need to test that material the same or nearly the same as the condition is work. We put the specimen on this kind of machine. It have the motor here. The motor gonna turning the head. So this one is going to twist, okay, and this one is going to fix heads, and then it's going to have the resisting torque. So we can measure the torque from the load dial, and also we can record the strain from this one. From the torque we have, we can determine the tau in which the shear stress is going to be T times R, and then divided by J. Okay, so we have the shear stress here, and we have the shear strain here. We can plot the graph for the shear stress, shear strain, and by doing the torsion, mostly we consider the square element on the surface of the shaft, and under the torsion, that element will change its shape. Okay, usually when start, this portion is rectangular, it is pi over 2 radian, and then after that the angle inside it change. The shear strain divided by the minus of what of the pi over 2 here, and with the zeta sub-palm. And for the torsional test, we obtain this shear strain. Some value on the shear strain that's important to us is the proportional shear strain, and also the G. The G is also very important for us. Okay, and for the design, we will use the tau allowable, and most of the tau allowable we determine. Okay, we set it equal to, actually it's tau sub y, which tau sub y can be estimated or set it into the tau sub proportion, and then it's divided by factor of safety. That is follow the chapter 5 of the mechanics of material. And next, okay, we go further to the Poisson ratio. Talking about the Poisson ratio is important because when we talking about the G, actually we can determine the G from the equation of E and then divide it by 2 times 1 plus the Poisson ratio. Okay, and next we go to the Poisson ratio. Poisson ratio is defined as the ratio of the lateral strain due to the axial strain. What is axial strain? When you pull this material, okay, the material will elongate. For example, we pull the elastic band, that's going to be the total elongation. And when you divide that elongation by the length, you get the longitudinal strain or axial strain. And at the same time, when you pull the rubber band, the lateral deformation also occur. That is going to occur by delta palm divided by 2 for this section. So if you divide that by the diameter, so we will get the lateral strain. Okay, that's going to be, this time is delta palm and divided by the diameter. However, this is the contraction, so this lateral strain supposed to be in minus. The Poisson ratio has specific value for a given homogeneous isotopic material. Homogeneous material is the material that's such as steel. It have the same molecule across its material. And isotopic is the property of material is free from the direction that force apply. If you cut steel in vertical and you cut steel in a horizontal, when you test it, it's going to have the same property. That's called the isotopic material. Okay, and then you got the lateral strain like this, you got the longitudinal strain like this, and then you put into the equation, you get the mu or nu for the Poisson ratio. So the Poisson ratio have the negative side here to adjust it to be the positive value. For the compression, if you compress this, the same thing, the lateral strain gonna be negative. However, when you compress it, the diameter gonna get larger, so the lateral strain gonna be positive. And then the same when you put into this equation, due to the negative side, the mu's always be positive. So consider this rubber band, and when you put it, it's going to change the shape like this. If we just consider the area here far away from the stress concentration on this supporting point, and if you take this one as the original length, this is going to be L sub O, this is going to be L sub F, and then you may determine the longitudinal strain on this problem to be what? To be L sub F minus L sub O, and then divide by the L sub O. At the same time, when you measure the width, okay, of this rubber band, this one gonna be original B, and then under the force, okay, you may determine the width of this rubber band again. You may get it to be B sub F. Okay, B sub F always less than B sub O. You may get lateral strain of what? Of B sub F minus B sub O divided by B sub O. This is going to be negative. And then you may determine the Poisson ratio as the lateral strain and then divided by longitudinal strain. For example of this rubber band. And then you did this in your lab for the laboratory too. Okay, finally we arrive at the last topic of this is the material failure due to the creep, due to the relaxation and to the fatigue. Okay, creep is kind of a material failure due to the permanent deformation of the material subject to the continuously increase to the deformation. For example, as a concrete. Concrete has the component of water, Portland cement, for example, sand and crushed stone. When you mix the concrete, there is the air void in the concrete, and in the air void there always water. And when the force applied to the concrete, what happens is the force will force the water move away or move out of the concrete, and then it's produce the permanent deformation of the concrete. It's not recoverable. For example, like this, that is the concrete with some water in the air. When you press it, okay, the water just come out. That's a model, and then the creep occur. The creep when occur in the concrete, it may make the concrete is look not beautiful, and a creep have very bad effect for the pre-stressed concrete. Due to the creep of the concrete have permanent deformation, and this will occur if the pre-stressed concrete beam shorten due to the creep, and then the force in the pre-stressed stand will also reduce, and the pre-stressed concrete cannot perform as its intended function. Next, the relaxation. The relaxation is a material failure is occur in the steel, especially the high strength steel, the pre-stressed steel. When you put the stress into the steel larger than 0.5 sigma sub y, what happens is the strain of the steel will relax itself. That means what? When you put the pre-stressed y with the sigma sub naught stress for some time, the stress that's inside it going to be reduced. That reduction is due to the movement of the grain of the steel. Okay, that is going to be also have the bad effect on the structure, such as the pre-stressed concrete structure, because when the pre-stressed stand have less stress, so the pre-stress effect will be reduced. The same thing as the creep. When the concrete creep, that means the concrete gonna shorten, and then when it's shortened, the stress in the pre-stressed steel or pre-stressed strand will reduce, and the effect of pre-stressing also reduce. And finally, we have a lab about the fatigue. For the fatigue, there are some structure in civil engineering, such as the steel bridge. When the car pass the bridge, okay, the bridge get deflect, and then when the car pass away, the beam of the bridge rebound back, and then it get repeat like this every time the car pass the beam defect. Every car pass the beam defect and rebound back, defect and rebound back. What happens is when the structural member or mechanical part subjected to that repeat the stress, which is less than, for example, sigma sub y, but due to the repeated load, there are micro crack there that's going to expand larger and larger, and when it reach some point, the steel will fail abruptly. That means the ductile material subjected to the repeated stress, which is less than the yielding stress, and is fail as the brittle material. We need to prevent this thing, especially in the structure such as the steel bridge. Okay, and the force that we have will fluctuate with the time, and one of the model of the force is the here. When we do the test in the fatigue test, we put the round specimen and bend it, and when we bend, the bottom gonna be in tension and the top gonna be in compression, and then the motor rotate the specimen, so the compression will start to be in tension, and the one that's in compression going to be in tension. So if there is cracks in the tension size, it's going to be close open, close open, close open, and it's going to get larger. If you cannot feel this, you may cut your finger with a small wound over there, and then you may push it up and down, up and down. You will feel that when you put it up, it's hurt a lot. The same thing occur as the steel, and then when it get bigger and bigger, there are less material resist the force, and then it fail directly. There are a lot of structure that's subjected to the repeated force, not only the beam in the bridge, the wing of the airplane also. When it fly, they are subject to the air, and then it's going to move a little bit up and down. It depends on how the wind act at it. When it's past some storm, it's going to swing a lot. Okay, we're going to consider that for the wing of the beam, and the breadth of the wind turbine also is going to have some kind of tension and compression, since this structure is a kind of cantilever structure, such as the same as the wing. Okay, and fatigue also occur in the wheel of the racing car, because it's subjected to the impact force also. It's repeated impact force make it crack. And due to we have the fatigue test, I got to mention about the SN diagram. In the lab, we're going to put the stress into the specimen. If the stress is large, the motor will spin less. When we put less stress, the number of spin of the motor until the failure of specimen gonna be large. There is a point for certain material that exhibit the endurance limit, in which is never failed by fatigue. And for the steel in this example, okay, having the sigma sub u of 820 megapascal, and from the test it show up the endurance limit of this steel is about half of the sigma sub u. This is a good news for the structural steel, because the structural steel going to have the yielding stress of 250, and then when we design the beam, we're going to use factor of safety about 2. So the allowable stress for the steel going to be 120 megapascal. That steel, structural steel, also have the ultimate stress of 400 megapascal, and if you use this approximate, the endurance limit of the structural steel is supposed to be 200 megapascal. So our allowable stress less than the endurance limit. So most of civil engineering structure are safe for fatigue due to the code specification. Okay. However, there are welding joints in the structure that are prone to the fatigue, because when you weld the structure, okay, the wheel always very hot, and some worker they just spray some water into that weld joints, and a lot of the time that weld joints crack, and it's a starting point of the fatigue. Okay, and this graph, the SN curve that you produce, also provide the fatigue strength. The fatigue strength going to tell you how much the structure can take the repeated force. For example, if you design the structure with the stress of 750 from this material, it's going to take about this. This one is a log scale. If you put like this, that's going to be about 200,000. Okay, 200,000. If you reduce the stress, design stress, to about 520, and then you put it up, you may get this one for this one's supposed to be 5 for the logarithmic scale. That is going to be 500. What does this one is? No, this is about 20,000. This is going to be 500,000. Okay, if it's going to be this, is going to be take a lot of number of repeated force. So this is called the endurance limit. Also, some materials such as aluminum, okay, they have a special SN curve in which no endurance limit show up. So by this material, you got to consider your structure carefully. How many repeated force gonna subjected to it during its life. For example, this you expect is going to take about a 1 million hit of the stress. You can decide it with the fatigue strength of 220. If this one going to take a 1 million hit of the repeated stress, if that's the case, you're going to decide it with the design fatigue stress about 160. Okay, you got to reduce the stress for the structure to withstand more repeated forces and stresses. Okay, what happened when you put the specimen into this? Okay, your specimen gonna be here, and then this one gonna push some force here, and then it's going to bend by the rotation of the motor here. Okay, this specimen gonna have tensile compressive stress, tensile compressive stress, like this for one specific point. What happened is the micro crack gonna get larger and larger and larger and larger until at specific time there are not enough material to take care of the force or moment, so it's going to crack and abrupt failure like this. Okay, that is the end of chapter 4. What we have from the start, we talking about the behavior of the material by take a look at the stress strain diagram, and you know the stress strain diagram for the tension test is going to have the vertical normal stress and horizontal normal strain, and from the stress strain you can classify the behavior of the material to be elastic behavior and plastic behavior. And also there are 4 regions in the ductile material. Okay, it's a elastic region in which when you pull it and you release the force, it's come back to the same length. It's a yielding, the second. The third is the strain hardening, and the fourth is the necking. And then we're talking about some specific mechanical property that are very important because the Thai industrial standard and the author standards specified it, which are the yielding stress, ultimate stress, modulus of elasticity, and the percent elongation. The percent elongation is important because it's used to classify the ductile material and the brittle material. And also, if your material didn't have the clear yielding stress, you're supposed to use 0.2% offset to determine the yielding stress. For the modulus of elasticity, you just determine the slope, okay, as the linear elastic portion of the stress strain diagram. You can get it. For the percent elongation, okay, you measure the fracture length or the length of the fracture. You may not with the original length divided by original length times 100. Most of the steel supposed to have percent elongation larger than 20% before its failure, because the structural steel is classified as the ductile material. Okay, and then we have some example to show the calculation, or to show when the structure, part of structure is in elastic and in plastic behavior, and you can calculate the deformation of the whole structure when subjected to the force, and you also calculate the deformation of structure when you release all the forces. And if the structure is elastic, the recover, they are going to recover. However, if structure is in plastic behavior, some of them will recover and they're going to have some permanent set, such as the steel column in the second example. And then we're talking about the shear stress, shear strain, since it is important because when you boring the rock or boring the soil to investigate the soil layer underneath our construction sites, you're going to use the shaft. The shaft is under the torsion, so you got to have the shear stress, shear strain diagram. You got to find the proportional shear stress, which usually approximate as the yielding shear stress, and you also need to find the shear modulus of elasticity. And then finally, before the final, we talking about the Poisson ratio, which is part of our laboratory tool. We take the laboratory to find the Poisson ratio of the rubber band, if you may recall. And then finally, we talking about the failure of specific thing, about the creep of the concrete, about the relaxation of the pre-tested steel, and finally, we talking about the fatigue of the structure, such as the steel beam on the bridge, in which steel beam subjected to the load from the truck that passed away 1,000 times a day. And luckily, in civil engineering, we use the sigma allowable lower than the endurance limit. So most of our structural steel that subjected to the repeat load are safe. However, there is some welding point that I just mentioned that we should be really careful about that. So for the fatigue, we can prevent it by doing some interval inspection and maintenance of those kind of the bridge. Okay, this is the conclusion of the chapter 4. We have discussed a lot about the mechanical property of the material.